Hi everybody, welcome back to Trigonometry. Today we're in section 5.1 talking about fundamental identities. So in this section we'll look at the fundamental identities, many of which we have already seen before and have already used. And we will also use identities to simplify trigonometric expressions, and we'll perform operations on expressions involving trigonometric functions. So that means like add, subtract, multiply, and divide. What these two objectives will be is pretty much the blend of trigonometry and algebra. So sharpen up your algebra skills and let's jump in. So first of all, you know several identities already, but let's go back over what an identity is. An identity is an equation that is satisfied by every value in the domain of its variable. So for example, here's an algebra identity. 2 times x plus 3 equals 2x plus 6. Now this is an identity because no matter what value of x you plug in here, both sides always have the same value. So one way you could look at it is you could say that every number is a solution of this equation. In other words, one side is identical to the other for every value of x that can be plugged in. Now we have already seen all the identities in this section except for the negative angle identities that we're about to learn. And you need to be aware that we will have an identity sheet for you to use on all the remaining tests in the class. So if you're taking this online, that would just be your final exam. But if you're taking this on campus, that would be test 3, test 4, and the final exam. So you'll have access to an identity sheet, but the identities from this section will not be on that sheet because they are fundamental identities. You should know them by heart. So all the identities that are in this section, be sure to memorize them. Now let's go ahead and get those negative angle identities that I mentioned earlier. The first one says that the sine of negative theta is equal to the negative sine of positive theta. So the way I like to say this is the sine of negative theta is equal to the opposite of the sine of theta. They'll have different SIGN signs. One will be positive and the other one will be negative. And because that's true for the sine function, the same thing is true for the cosecant function. So the cosecant of negative theta is equal to the opposite of the cosecant of positive theta. Now for cosine, it works differently. The cosine of negative theta is equal to the cosine of positive theta. It looks like the negative sign just disappears. And the same thing is true for secant. The secant of negative theta is equal to the secant of positive theta. Okay, so just to recap, when you have the sine of a negative angle or the cosecant of a negative angle, it looks like you can take the negative from the argument and pull it out front. That's not really what's happening, but that's what it kind of looks like. But on the cosine and the secant, it looks like the negative just disappears. Okay, so now how will tangent and cotangent behave? They behave like the sine function. So the tangent of negative theta is equal to the opposite of the tangent of positive theta, and the cotangent of negative theta is equal to the opposite of the cotangent of positive theta. Okay, now let's practice with that a little bit in example 1. So here it says if the tangent of theta is equal to 2.6, then the tangent of negative theta is equal to blank. Well, we know from our negative angle identities that the tangent of negative theta is equal to the opposite of the tangent of theta. So if the tangent of theta is 2.6, the opposite of that is negative 2.6. And then on part B it says if the cosine of theta is negative 0.65, then the cosine of negative theta is blank. And so let's think about the negative angle identity for cosine. We know that the cosine of negative theta is equal to the cosine of positive theta. So if the cosine of positive theta is negative 0.65, then the cosine of negative theta is also negative 0.65. And then let's look at part C. And it says if the sine of theta is equal to 2/3, then the negative sine of negative theta is equal to blank. Okay, so let's just leave the negative right here, and then let's think about the sine of negative theta. We know that the sine of negative theta is equal to the opposite of the sine of positive theta. And now that we've written it like this, you probably can see that negative times negative is going to make positive. So the answer here is really just the sine of theta, which we know already is 2/3. Okay, now let's take another look at the reciprocal identities. You've already seen these and you've been using them all semester, so there's nothing new here, but let's just write them down again. So we know that the sine of theta is equal to 1 over the cosecant of theta, and that means that the cosecant of theta is equal to 1 over the sine of theta. The secant of theta is equal to 1 over the cosine of theta, which means that the cosine of theta is equal to 1 over the secant of theta. And the tangent of theta is equal to 1 over the cotangent of theta, and that means that the cotangent of theta is also equal to 1 over the tangent of theta. Now in the past, we have used these identities many times to evaluate function values. So for example, if you knew that the tangent of theta was 3/4, then you knew that the cotangent of theta was the reciprocal of that, so you knew that the cotangent then would be 4/3. We're used to using these identities in that way, but now we're going to be using them to simplify expressions. So notice this. Every function that you see written on the left side of an equal mark here is the numerator of a fraction, and the denominator of each of those fractions is 1. So you could look at it this way. Having the sine of theta as a factor in the top of an expression is equivalent to having cosecant of theta as a factor in the denominator of that expression. And the other way around, having cosecant of theta as a factor in the top is equivalent to having sine of theta as a factor in the bottom. And the same thing is true for the rest of these functions. So as long as we're working with one term at a time, we can restate expressions by replacing a function in the top of a fraction with its reciprocal function in the bottom of that term. Or we can replace a function in the bottom with the reciprocal function in the top. And like I said before, this is true for any of the functions, but our usual strategy is to try to eliminate secant, cosecant, and cotangent by restating them in terms of sine, cosine, and tangent. And that allows us to see what functions can be divided out, if any. So here's example 2, and let's just practice using our reciprocal identities to simplify each of these expressions. In part A, we have the sine of x times the cosecant of x. Now remember, there's a denominator of 1 here, so every expression can be thought of as a fraction, and if it doesn't have a denominator, you can give it a denominator of 1. Now, like I said before, our usual strategy is to eliminate cosecant, secant, and cotangent by rewriting them in terms of sine, cosine, and tangent. So we're going to use our reciprocal identity for cosecant and say that having cosecant of x in the top is equivalent to having sine of x in the denominator. So this sine of x we're going to leave in the top of our expression, and this cosecant of x we're going to rewrite as the sine of x in the denominator. And now that we have sine of x divided by itself, we know that anything divided by itself is 1, so that will cancel out and leave 1. Let's look at part B. Here we have tangent of x divided by the cotangent of x. So again, let's follow our strategy of rewriting cosecant, secant, and cotangent in terms of sine, cosine, or tangent. So this time what I'm going to do is leave this tangent of x in the top of this expression, and I'm going to rewrite cotangent of x from the denominator as tangent of x in the top. So now I have tangent of x times tangent of x, which is tangent squared. And now let's get our quotient identities, and you've seen these before as well. You might remember from the end of chapter 1, the tangent of theta is equal to the sine of theta divided by the cosine of theta. And the cotangent of theta then, being the reciprocal, is going to have to be equal to cosine of theta divided by sine of theta. These are the quotient identities. Now, why are these true? Well, let's just take the first of these quotient identities and let's see if we can find out why the tangent of theta is equal to the sine of theta divided by the cosine of theta. Well, we know that the definition for tangent of theta is y over x. And now we also know that when we have a fraction, we can multiply the top by anything as long as we also multiply the bottom by that thing. It's the same thing you do when you're getting a common denominator. So if I choose to multiply top and bottom by 1 over r, then the top of this expression now becomes y times 1 over r, which is y over r, and the bottom becomes x times 1 over r, which is x over r. Now y over r is the definition of the sine of theta, and in the denominator, x over r is the definition of cosine of theta. So now you can see the tangent of theta equals the sine of theta over the cosine of theta. And you could do the same thing for the other quotient identity and it would work exactly the same way. Now let's take a second to compare the reciprocal identities and the quotient identities. It is important that you be able to tell these apart. So let's remember that the word quotient means division. And so the quotient identities are the ones that show a division. So like tangent of theta is equal to sine of theta divided by cosine of theta. The fact that we have one quantity divided by another quantity is how these got the name quotient identities. But the reciprocal identities all involve a reciprocal. In other words, they all have 1 over a function. So here are 3 of our reciprocal identities right here. The cosecant of theta we know is 1 over the sine of theta, or we could say the cosecant of theta is the reciprocal of the sine of theta. Secant of theta is the reciprocal of cosine of theta. Cotangent of theta is the reciprocal of tangent of theta. So you can see how these got their name of reciprocal identity. And you know that this is just 3 of our reciprocal identities. There are 3 others. So now let's look at example 3 together. So let's read the instructions. It says restate each expression in terms of sine and cosine, and then simplify so that no quotient remains. On each step, state what kind of identity was used. Now I put this in the instructions for example 3 because I think it's a really good idea for you to get into the habit of justifying, at least in your mind, why you're doing each step. It doesn't matter so much in section 5.1 about writing why you're doing each step, but when we get to section 5.2, you will have to write down why you're doing each step. So we may as well practice it a little bit here. So let's take part A here. We have cosine of theta times cosecant of theta. And remember, we want to restate these expressions in terms of sine and cosine. So the first thing I notice is that we have a cosine of theta here. That's fine. But this cosecant of theta right here, I want to restate in terms of sine and cosine. So I need to use a reciprocal identity to write this in an equivalent form. So we know that having cosecant of theta in the top is equivalent to having sine of theta in the bottom. So for our first step, let's leave cosine of theta in the top, and let's rewrite cosecant of theta as sine of theta in the denominator. Now, what kind of identity did we use to make that move? We used a reciprocal identity, so we just need to write that down. And now the instructions say simplify so that no quotient remains. Well, of course, this is a quotient because it's one thing divided by another thing. So this can't be left in this form. But we remember that we have an identity that says cosine of theta over sine of theta is equal to cotangent of theta. What is the name of the identity that lets us change this quotient into a cotangent function? Well, that was one of our quotient identities that let us do that. So this is what we mean when we say state what kind of identity was used. It just means you need to justify your thought process or say what kind of identity gives you permission to do the step that you did. Okay, now let's look at part B. So here we have secant of theta divided by cosecant of theta. So both of these we want to restate in terms of sine and cosine. So we know we'll still have a fraction bar. And let's start by rewriting this cosecant of theta in the denominator as its reciprocal function in the top. So cosecant of theta in the bottom is equivalent to sine of theta in the top. And we also know that secant of theta in the top of an expression is equivalent to cosine of theta in the bottom. Now, what kind of identity let us swap these two functions out for these two functions? Those were reciprocal identities that we used to do that. Okay, now because we can't leave a quotient in our final form, we need to think about whether we can rewrite this as some other function. So we know from our quotient identities that sine of theta over cosine of theta is equal to tangent of theta. And so now I just want to write down that the reason I was able to do that step is because I used a quotient identity. Okay, now continuing example 3, in part C we have tangent of negative theta divided by secant of theta. So I believe the first thing I would do here is use one of our negative angle identities to eliminate this negative inside the argument. So we remember that the tangent of negative theta is equal to negative tangent of positive theta. And for this step, I'll just leave the secant of theta where it is. And I'm going to write down that I used a negative angle identity to move this negative sign. Okay, now let's address this secant of theta in the denominator. So we know that secant of theta in the bottom of an expression is equivalent to having cosine of theta in the top of that expression. So I've still got my negative tangent of theta here, but I've rewritten secant of theta in the bottom as cosine of theta in the top. And the reason I'm able to do that is because we have a reciprocal identity that says that's true. Okay, now in order to see what can be simplified here, we have to finish expressing this in terms of sine and cosine. So now let's restate tangent of theta as its quotient form. So I'm going to keep my negative sign here, and then we'll have tangent of theta written as sine of theta over cosine of theta. So now we have a denominator. And this cosine of theta that we already had is in the numerator. It's in the top. Now what kind of identity let me change tangent to sine over cosine? That was a quotient identity. And now we can see that cosine in the top cancels cosine in the bottom. And I'm just going to write down that I reduced. So we're continuing to justify our thought process all the way through. And now what's left is just negative sine of theta. And so that is completely simplified. Let's look at part D. So here we have tangent of theta times cosecant of theta. And we know we want to write these in terms of sine and cosine, and you could handle either one of them first. I'll just take the tangent of theta first. So I know that tangent of theta is equal to sine of theta over cosine of theta, and I'm just going to write down that I used a quotient identity to rewrite tangent of theta as sine of theta over cosine of theta. Now nothing reduces here, so now we want to use a reciprocal identity to restate cosecant of theta in terms of sine. And we know that cosecant of theta in the top of an expression is equivalent to sine of theta in the bottom of that expression. So now we'll still have sine of theta over cosine of theta just like they are, and we'll rewrite cosecant of theta in the top as sine of theta in the bottom. And that was a reciprocal identity that let us do that. Now we see that sine of theta is a factor of both the top and the bottom, so we will cross those out and write that we reduced there. Of course, anytime you cross out all the factors from the top, there's always a factor of 1 that remains. So now that we've reduced, what we're left with is 1 over cosine, and we know that we can't leave our answer in this form because it says simplify so that no quotients remain. So we need to restate this where it doesn't require a denominator. And we know that having cosine in the denominator of an expression is equivalent to having secant in the top of that expression. So 1 over cosine of theta becomes secant of theta, and we were able to do that because of a reciprocal identity. Okay, now continuing in that vein, let's look at example 4. And the instructions here say write each expression in terms of sine and cosine, simplify so that no quotients appear in the final expression, and all functions are of theta only. Now, whenever they say all functions are of theta only, they mean that you can't leave things like sine of negative theta or something like that. All your functions have to only be whatever function of theta. And notice that here the instructions do not say anything about having to write down which identity you're using. So this time we'll just talk through it and we won't necessarily write down what we're doing. So in part A, we have cosecant of theta times cosine of theta times tangent of theta. And I say that we just take these one at a time and apply the reciprocal or quotient identities as we go. So we know that we're going to end up with a denominator here, so we know we're going to need a fraction bar. And now let's rewrite cosecant of theta, which is in the top of this fraction, as sine of theta in the bottom of our new fraction. So cosecant in the top is equivalent to sine in the bottom. The second factor is cosine of theta. Well, that's already written in terms of sine or cosine, so we just need to leave that alone. So I'll just copy it into the top there. And then for tangent of theta, we know that our quotient identity says we can restate that as sine over cosine. And then we see a top-bottom pair of cosines, so those will divide out. And we see a top and bottom pair of sines, and so those will divide out. And we know that whenever everything divides out, you're left with 1. So this whole expression simplified to 1. And then for part B, we have in parentheses sine of theta minus cosine of theta times parentheses cosecant of theta plus secant of theta. And I'm sure it does not escape you that this looks like something we could use the FOIL method on. And that is exactly what we have. So we're going to apply the FOIL method to multiply these two factors together. And then we'll use our reciprocal identities and quotient identities to do whatever we can to simplify it. So let's start at the beginning. So FOIL, first times first, is going to be sine of theta times cosecant of theta. Outer times outer is going to be sine of theta times secant of theta. And then inner times inner, we have negative cosine of theta times cosecant of theta. So that's going to be minus cosine of theta times cosecant of theta. And I went to a second line here just because I was running out of room. And then for last times last, we have negative cosine of theta times secant of theta. So we will write minus cosine of theta times secant of theta. Now let's go back, and for each one, let's see what we can do with reciprocal identities. In this first term, remember we have to work one term at a time when we're using reciprocal and quotient identities. So in this first term, we have sine of theta times cosecant of theta. Cosecant of theta in the top can be rewritten as sine of theta in the denominator. So now we have sine of theta over sine of theta. The next term, so plus sine of theta, and then this secant of theta that was in the top is going to be rewritten as cosine of theta in the bottom. Okay, next term, minus cosine of theta times cosecant of theta. We will restate this cosecant of theta in the top as sine of theta in the bottom. So we'll have minus cosine of theta over sine of theta. And then minus cosine of theta times secant of theta. We know that we will rewrite this secant of theta in the top as cosine of theta in the bottom. So we'll have minus cosine of theta over cosine of theta. Now let's see what else we can do here to simplify. So we know that sine of theta over itself is going to reduce to 1. And then for the second term, we know that sine of theta over cosine of theta can be restated as tangent of theta, and we needed to do that because it says that no quotients should appear in the final expression. And then we have minus cosine of theta over sine of theta. We know that's equivalent to cotangent. And then we have minus cosine of theta over itself. Well, anything over itself is 1. And so now we have 1 plus tangent of theta minus cotangent of theta minus 1. And we can see that if we combine like terms, the 1 and the minus 1 will add up to 0. And we will just be left with tangent of theta minus cotangent of theta. Now let's pick up our last set of identities for this section, and these are the Pythagorean identities, which you also may remember from the end of section 1.4. So I'm just going to give them to you, and then we'll talk about them. Sine squared of theta plus cosine squared of theta equals 1. Tangent squared theta plus 1 equals secant squared theta. And 1 plus cotangent squared theta equals cosecant squared theta. Now, it is very important that you memorize these. So let's take a look. Sine squared theta plus cosine squared theta equals 1. You may be pretty familiar with that one. I think we've seen it a couple of times now. That one's really not hard to memorize. I don't think you'll have any trouble with that. But I think a lot of students have trouble keeping these two separated because they are kind of similar and they're a little harder to memorize. But let's just keep in mind that for both of these, the one is on the left side of the identity, and one of them involves tangent squared and secant squared, and the other one involves cotangent squared and cosecant squared. So in one of them, both of the functions have co in front of them, and in the other one, both of the functions don't have co in front of them. And so if you can just remember that tangent squared and cotangent squared both belong on the left side of their identity with the plus 1, then you'll know that on the other side of the equal mark, you'll either have secant squared or cosecant squared. And the secant squared goes in the same identity with tangent squared, and the cosecant squared goes in the same identity with cotangent squared. So now let's talk about why these identities are true. And we've seen this before, but I think it's worth going back over to help you really understand what's happening here. So we remember the old basic Pythagorean theorem. Y squared plus x squared equals r squared. If we were to divide through by r squared, and notice it does have to be r squared, not just r, but r squared, then because both the top and bottom have the same exponent here, we can write this fraction in parentheses with one exponent outside. So now we have y over r squared plus x over r squared, and that's going to equal 1 on the right side because r squared divided by r squared is 1. And now we know that y over r is sine, so y over r squared is sine squared theta. And we know that x over r is cosine, so x over r squared is cosine squared theta. And then the sum of those two equals 1. We could do a similar thing to come up with the second Pythagorean identity. So this time we want the y squared to become tangent squared, so let's divide through by x squared. So now y squared over x squared can be written as y over x all squared. X squared over x squared reduces to 1, and on the right side of the equal mark we'll have r over x squared. Now we know that y over x is tangent, so y over x squared is tangent squared theta. Then we have our plus 1, and then on the right side, r over x represents secant. So r over x squared is secant squared theta. And there's our second Pythagorean identity. And let's just go ahead and get the third one. So we've already divided through by r squared to get the first identity, x squared to get the second identity, and now let's divide through by y squared to get the third identity. So if we divide each term by y squared, then y squared divided by itself is 1. X squared divided by y squared can be written as x over y all squared. And then on the right side of the equal mark, r squared over y squared is r over y all squared. Now, x over y is cotangent, so now we have 1 plus cotangent squared theta equals r over y squared, and we know r over y is cosecant, so that's going to give us cosecant squared theta. And so you can see how these identities got their name. They're called the Pythagorean identities because they're all based on the Pythagorean theorem. Now we will frequently see expressions that involve one or two terms from a Pythagorean identity, so it's important for us to be able to recognize their alternate forms. So let's take our original sine squared theta plus cosine squared theta equals 1, And let's rearrange this so that the sine squared term is isolated. So to do that, you would subtract cosine squared from both sides. And now we can see that sine squared theta is going to be equal to 1 minus cosine squared theta. So this is an alternate form of that original identity. I do not want you to memorize this necessarily, but you should work with it until it's familiar to you. And what you should be able to do is take your original identity that you're going to memorize and rearrange it to isolate any term that you want. Let's take the same identity again and this time isolate the cosine squared term. So if you wanted to isolate the cosine squared, you'd have to subtract sine squared from both sides. And that would leave you with cosine squared theta equals 1 minus sine squared theta. And now let's take the identity that involves tangent squared theta. So that would be tangent squared theta plus 1 equals secant squared theta. Well, if we want to isolate the tangent squared term, we'll have to subtract 1 from both sides. And that would leave us with tangent squared theta on the left is equal to secant squared theta minus 1 on the right. And finally, let's take our third Pythagorean identity that involves cotangent squared of theta, and let's isolate the cotangent squared term. So we start with 1 plus cotangent squared theta equals cosecant squared theta. If we want to isolate the cotangent squared term, we'll have to subtract 1 from both sides. And that would leave us cotangent squared theta on the left equal to cosecant squared theta minus 1 on the right. Now you might be wondering why those alternate forms are so important. So here's the deal. Anytime an expression contains one side of a Pythagorean identity, you can replace that expression with the other side of the identity. It's like having interchangeable parts. So let's look at this example together. Here we have 1 minus cosine squared theta all over sine of theta. One thing we can do is notice that this is a Pythagorean expression right here. So anytime you see a 1 in a squared function, it should make you think of a Pythagorean identity. And so we want to think of the identity that involves cosine squared theta. And that was this one, sine squared theta plus cosine squared theta equals 1. And you want to ask yourself, can I rearrange the terms in my identity so that one of the sides looks like what I see in my problem? And in this case, it's pretty easy to get 1 minus cosine squared theta. All we would need to do is move this cosine squared theta to the other side of the equal mark. And so we'll just subtract cosine squared theta from both sides, and then we'll have sine squared theta equals 1 minus cosine squared theta. So we can take this 1 minus cosine squared theta out of our problem and replace it with its equivalent, which is sine squared theta. So I can rewrite this expression as sine squared theta over sine of theta. You see how 1 minus cosine squared theta was replaced by sine squared theta because our identity says they are equal to each other. And now I'm going to be able to reduce this. So let me rewrite sine squared theta as sine of theta times itself, and then we still have this sine theta in the bottom. And you can probably see that one of the sines in the top is going to cancel the sine function in the bottom, and that just leaves us with sine of theta in the top. So this whole expression simplified to sine of theta because we made this Pythagorean substitution right here. So in example 5, let's use the Pythagorean identities to restate the expressions below and then simplify so that no quotients remain. And we'll start with part A, and it says 1 plus cotangent squared theta all over 1 minus cosecant squared theta. So the first thing we notice is the top looks like part of a Pythagorean identity. It has a 1 and it has a squared term. So we want to recall from memory which Pythagorean identity contains cotangent squared. So I'm just going to jot that down here. It was 1 plus cotangent squared theta equals cosecant squared theta. Now, this already has the left side identical to the top of the expression we're working on. So I can make that straight substitution. But I also notice that the denominator uses the same identity. So let's go ahead and rearrange our identity here so that we have this 1 minus cosecant squared that we'll use for the denominator. So in order to rearrange these terms so that one of the sides has 1 minus cosecant squared theta, I'm going to need to leave this 1 positive and bring this cosecant squared theta over here. And then I'm also going to have to bring the cotangent squared theta to the right side. So that would become 1 minus cosecant squared theta equals negative cotangent squared theta. Okay, now let's do our substitution. The top expression, 1 plus cotangent squared theta, we see can be replaced with cosecant squared theta. And the bottom expression, 1 minus cosecant squared theta, we see down here can be replaced with negative cotangent squared theta. Now there are multiple ways that you could move forward from here. My favorite way is to get rid of all the cosecants and cotangents and write in terms of tangent and sine first, and then we can go to terms of sine and cosine if we need to. So what we're going to do now is keep our negative. We know positive divided by negative is negative, so we don't want to lose our negative sign. I'm going to put it right here in the top where I won't lose it. And I'm going to restate cotangent squared from the bottom as tangent squared in the top. That's because we have a reciprocal identity that says that cotangent in the bottom of an expression is equivalent to tangent in the top of that expression. And now the cosecant squared in the top will be rewritten as sine squared theta in the bottom. And again, that's that reciprocal identity at work. Okay, now I still can't reduce, but I do know that I can restate tangent as sine over cosine. So now this is tangent squared. So it's going to be rewritten as sine squared over cosine squared. Here we go. Don't lose your negative. Keep that negative right there. Tangent squared theta is going to be rewritten as sine squared theta over cosine squared theta. And then this sine squared theta that was in the denominator is still there. Okay, now we have sine squared theta in the top and sine squared theta in the bottom. They will cancel each other out. And again, anytime that all the factors cancel out of the top, there's always a 1 that remains. So now we have negative 1 over cosine squared theta, and we can't leave this in quotient form. So now we use a reciprocal identity to restate this so that cosine squared from the bottom is rewritten as secant squared in the top. But again, don't lose your negative. So that will be equal to negative secant squared theta. Now here's part B. And here we have secant squared theta minus 1 all over cosecant squared theta minus 1. So first we would want to take a look at the Pythagorean identity that involves secant squared. So come down here at the bottom and kind of use it like a little piece of scratch paper. And I've just written out the identity that involves secant squared theta. So it's tangent squared theta plus 1 equals secant squared theta. Now I want to rearrange these terms so that one side of the identity has this expression. So all I need to do is take the plus 1 and move it to the right side, and we'll see that tangent squared theta equals secant squared theta minus 1. So that's the substitution we'll make in just a minute. But let's go ahead first and look at the denominator of our expression. So it has cosecant squared theta minus 1. So we'll want to remember first the Pythagorean identity that involves cosecant squared theta. And here it is. 1 plus cotangent squared theta equals cosecant squared theta. And I want to rearrange these terms so that one side of the equal mark has cosecant squared theta minus 1. And again, it's not hard to do. All I need to do is bring the 1 over to the right side of the equal mark where it will become negative. So that will give us cotangent squared theta equals cosecant squared theta minus 1. Okay, now to make our substitutions. In the top, we said secant squared theta minus 1 would be replaced by tangent squared theta. And in the bottom, we said cosecant squared theta minus 1 would be replaced by cotangent squared theta. Okay, now there's no reducing that we can do at this point, so let's use a reciprocal identity to get rid of this denominator. We know that cotangent in the denominator can be restated as tangent in the top. So leaving our tangent squared theta that we already had in the top, we now will have cotangent squared theta from the bottom rewritten as tangent squared theta in the top. And now that all the functions are in the top of the expression, there's no denominator visible, and we can see that nothing is going to cancel out. So we just have to finish the multiplication. Tangent squared theta times tangent squared theta is, of course, tangent to the fourth of theta. Now let's talk about a few algebra techniques, and the first one is going to be common denominators. So we will frequently be asked to add two trig functions together. And the way that you add or subtract two trig functions is by finding a common denominator so that the expression can be written as a single term. It says do the addition or do the subtraction, but it doesn't actually feel like adding and subtracting to you. It's not like adding whole numbers together like 3 plus 5 equals 8. It's more of finding the common denominator for those two trig functions. And the good news is that finding a common denominator for trig functions is done the same way as finding common denominators for real numbers. All you have to do to change a denominator is multiply the top and bottom by the same thing. Let's practice here in example 6. So it says perform the operation, simplify the expression so that no quotients appear, and all functions are of theta only. So we have cosecant theta minus sine of theta. And you might be thinking, I don't know how to add and subtract trig functions. But what you have to know is you really can't add them directly. All you can do is get a common denominator so that they can be combined into one expression. So we need to restate cosecant of theta in its reciprocal form so that we have a denominator to work with. So let's write cosecant of theta as 1 over sine theta, and then this minus sine theta stays the same. And now we have a denominator that we can work with. So if we need a common denominator, this second term needs to have the same denominator as the first term. So in order to create that sine of theta denominator, we'll have to multiply top and bottom of this term by sine of theta. Okay, now that they've both got the same denominator, I'm going to write them as one single fraction. So the bottom of our new fraction will be sine of theta. That's why we got a common denominator, because you know when you add fractions, the denominator stays the same. Okay, but now the top of our new fraction will be 1 minus sine squared of theta, because sine of theta times itself is sine squared theta. So the new top of our fraction is 1 minus sine squared theta. Okay, now remember that they said simplify the expression so that no quotients appear. So we will need to eliminate this denominator somehow. And the best thing I can see to do is look at the top of our expression here. Do you see how that looks like part of a Pythagorean identity? It should look familiar to you because it has a 1 and a squared function. So that should kind of be a little indicator to you that we might be able to make a Pythagorean substitution here. Let's come over here in the corner and think about the identity that involves sine squared theta. So I've written it here, sine squared theta plus cosine squared theta equals 1. And I want to rearrange these terms so that one side looks like 1 minus sine squared theta. Of course, all I need to do, because I already have a 1 on the right side, is I just need to subtract sine squared theta from both sides. So that will give us cosine squared theta equals 1 minus sine squared theta. So now I can see that this 1 minus sine squared theta can be replaced by cosine squared theta. And I still have this sine of theta in the denominator. Now you might be thinking, well, we still have a denominator here. I thought we were going to try to get rid of the denominator. And we do have to do that. So now what we'll do is we'll separate this cosine squared theta into cosine theta times itself. And I just did that so you could see what's about to happen. we're going to kind of group together this cosine theta over sine theta and leave this other cosine theta out here. Now the reason I grouped these together is because you'll recognize cosine theta over sine theta is equivalent to cotangent theta, right? So now this part can be rewritten as cotangent theta times cosine theta. And now we have performed the operation, which was subtraction, and we have simplified the expression so that no quotients appear and all the functions are of theta only. So we have cotangent of just theta and cosine of just theta. Another algebra technique we want to look at is splitting a quotient into two terms. So if the top of a quotient contains multiple terms, then the quotient can be split into separate terms where each term is over the same denominator. Let me give you an example from just basic algebra. If we had, for example, x over 5 plus 1 over 5, you are probably already comfortable saying that these can be written as one fraction. And since the denominator is 5, the denominator of the new expression would be 5, and the top would just be x plus 1. That's not a problem for us, right? But did you know that we can go the other direction as well? So if we have x plus 1 over 5, we can split it back up into these two parts. Because the top of our expression contains two terms, we can split this up into two separate fractions. The first fraction would be x over 5, and then there would be a plus sign, and the next fraction would be 1 over 5. So we're going to use this to our advantage to help us simplify trig expressions. Here's example 7. And again it says simplify the expression so that no quotients appear and all functions are of theta only. And so we have 1 plus tangent theta all over tangent theta. Now I want you to notice something before we get started. A lot of students will see the 1 in the tangent theta, and they will think that looks like my Pythagorean identity that says 1 plus tangent squared equals secant squared. And it does look a little similar to that, but this function is not squared, so we can't use that identity. But what we can do is say, oh, I've got a plus sign here. And because I have a plus sign, I can split this into two separate fractions. The first fraction will be 1 over tangent theta, and then there'll be a plus sign. And the next fraction will be tangent theta over tangent theta. And then we should simplify each one separately. So of course 1 over tangent theta can be restated as cotangent theta. And then we have our plus sign. And then we notice that tangent of theta over itself can be reduced because tangent of theta divided by tangent of theta is equivalent to 1. And so we have, for our final answer, cotangent of theta plus 1. That's not hard to do, right? This is one of my favorite strategies to use, is to split the fraction into two terms and simplify separately. And now let's talk about the distributive property. You are very familiar with the distributive property from algebra, and it works the same way here. Now sometimes you'll want to distribute something like tangent or secant, and so you can choose to restate your functions in terms of sine and cosine before you distribute or after you distribute. Most students prefer to distribute first and then restate in terms of sine and cosine at the end. That is your call. So here's example 8. Same instructions. It says simplify the expression so that no quotients appear and all functions are of theta only. And the expression is cosecant of theta times parentheses cosine of theta minus tangent of theta. Now, like I said, you could restate this as 1 over sine theta first and then distribute that if you want to, but most students prefer not to distribute a fraction. So you can distribute it just exactly the way it is here. And let's do that. So first we'll have cosecant of theta times cosine of theta, and then we'll have a minus sign, and then we'll have cosecant of theta times tangent of theta. Okay, now let's work on each term separately and apply our reciprocal identities and quotient identities. For the first term, we know that cosecant of theta in the top can be restated as sine of theta in the bottom. So let's go ahead and put our fraction bar and put sine of theta in the denominator. And then this cosine of theta will just stay in the top. Then we have our minus sign. And again, for this term, we will restate cosecant theta in the top as sine of theta in the denominator. And then we'll restate tangent of theta as its quotient identity. So tangent of theta will become sine of theta over cosine of theta. Now let's see what we can do to simplify so that no quotients appear. For the first term, we know that cosine of theta over sine of theta can be written as cotangent of theta. That's a quotient identity that lets us rewrite that. And then we have our minus sign. And for the second term, we see that sine of theta in the top will cancel sine of theta in the bottom and leave a 1 in the top. And so that would be 1 over cosine theta, but we know that this has to be restated so that no quotients appear. So we need to use our reciprocal identity to say that cosine of theta in the bottom is equivalent to secant of theta in the top. And so we end up with cotangent of theta minus secant of theta. Now let's talk about a few illegal moves when simplifying. Sometimes understanding what you can't do helps you understand what you can do even better. And I think this is one of those times. So the first illegal move we're going to look at is this. If there are terms within a fraction, we cannot use reciprocal identities or quotient identities on the whole fraction. That's because we can only use reciprocal and quotient identities when the fraction is all one term. This example right here, where we have 1 plus sine of theta all over cosine of theta, has 2 terms in the top. Because of the plus sign, we know that the top is made of 2 separate terms. Now what a lot of students want to do here is they want to say, oh, I see that sine theta over cosine theta makes tangent theta. And so they just leave the 1 out front and say sine of theta over cosine theta is tangent. But that is not allowed. We cannot do that because sine of theta is not a factor of the top. It is a term in the top. And so it's not free to combine in that way. Instead, what we can do here is we can split the fraction into 2 separate terms. So we can take advantage of the plus sign to separate this into 2 separate fractions like so, and then we can say 1 over cosine is secant and sine over cosine is tangent, and so we would end up with secant theta plus tangent theta. Illegal move number 2 is that we cannot split up denominators by terms. So we know that we can split up numerators by terms like we just did in the last example. And so sometimes students will think that they can split up denominators by terms. So what they'll try to do is they'll say, oh, I'm going to split this denominator, so I'm going to have tangent squared theta over cosecant squared theta and then minus tangent squared theta over 1. See, they split that denominator. But that's not how denominators work. So this is not allowed. Instead, a better way to handle a problem like this would be, if you've got 2 terms in the denominator, see if you can make a Pythagorean substitution. Here we know that cosecant squared theta minus 1 makes us think of our Pythagorean identity 1 plus cotangent squared theta equals cosecant squared theta. And this can be rearranged so that we have cosecant squared theta minus 1 is equal to cotangent squared theta. We would replace these 2 terms with cotangent squared theta and then use a reciprocal identity to end up with tangent to the 4th theta. And I know I'm going through this kind of fast, but that's because we've already used this strategy in a previous example. I'm mostly focused here on showing you what you can't do. And then I just want you to see what strategy you can use. And as you practice, you'll get better and better at using these strategies. Okay, illegal move number 3. We cannot take square roots term by term. In other words, we cannot just remove exponents from the Pythagorean identities. So, for example, we know that cotangent squared theta plus 1 equals cosecant squared theta. That's one of our Pythagorean identities. But we cannot just then remove those exponents and say that that means that cotangent theta plus 1 is cosecant theta. That's not how it works. So, for example, if you were working on 1 plus tangent theta all over secant theta, you might look at this and think, oh, that almost looks like a Pythagorean identity. And you might start to think 1 plus tangent squared equals secant squared. So does that mean 1 plus tangent theta equals secant theta? And so a lot of times what students will do is they'll replace this 1 plus tangent theta with a secant theta, and then they'll reduce that to 1. But that is not how it works. You can't just take the exponents off. If you could, we wouldn't even have a Pythagorean theorem at all. Instead, what we want to do here is, again, take advantage of that plus sign in the top to split this into separate fractions. So we could say 1 plus tangent theta over secant theta would split up into 1 over secant plus tangent over secant, and then we could rewrite 1 over secant as cosine theta, and we could rewrite tangent theta over secant theta as sine over cosine, and then restate secant in the bottom as cosine in the top, and then you can see the cosines would cancel, and we would be left with cosine theta plus sine theta. Now, some of the problems that we will see in this section ask us to use a given value to find other values. We have already done this before. We learned how to do it using the function definitions back in chapter 1. So we're still going to do it that way. If you look at one of these problems in my lab and you click on the online help, they're going to ask you to do it by using the identities, usually the Pythagorean identities and the quotient identities. But the easiest way to do it is using the definition, so that's how we're going to do it so that we can avoid all of the algebra that goes with plugging into the identities. So here's example 9, and it says if the tangent of theta equals negative 5 over 3, and theta is in quadrant 2, find each function value. So do you remember seeing problems like this earlier? Yes. Okay, so what they really intended for us to do here was to make the link between tangent and secant and say, oh, we have a Pythagorean identity that involves tangent squared and secant squared, and then you would just plug into that identity and solve for secant. But there is an easier way. So we know that theta is in quadrant 2. Let's draw ourselves a quadrant 2 angle, and then let's close up our little angle here so that we get a right triangle. And then we know that the tangent of theta is negative 5/3. So if we think about the definition of tangent, that's y over x. So what they're giving us here is that the vertical side of the triangle is 5 and the horizontal side of the triangle is 3. And now we just want to find r here using the Pythagorean theorem. Now you might be tempted to say that this is a 3, 4, 5 triangle and that this missing hypotenuse length would be 4 because we have the 3 and the 5. But that would be wrong, because whenever you have a 3, 4, 5 triangle, you know the hypotenuse has to be the 5. This hypotenuse has got to be something bigger than 5 because 5 is one of our legs. So we'll want to add the squares here. 5 squared is 25, 3 squared is 9, 25 plus 9 is 34, so this hypotenuse length is square root of 34. Okay, now to find the secant, we know that the definition of secant is r over x. And we know that for a quadrant 2 angle, only sine and cosecant are positive, so secant's going to have to be negative. So secant of theta for this angle is going to be negative r over x. So that's negative square root of 34 over 3. Now for part B, they've asked us to find the cotangent of negative theta. Now they gave us the tangent of positive theta in the problem. So it's easy for us to use this value to get the cotangent of positive theta. We know that the cotangent of positive theta would be negative 3 over 5. But now to get the cotangent of negative theta, we need to remember the negative angle identity. And that says that the cotangent of negative theta is equal to the opposite of the cotangent of positive theta. Well, the cotangent of positive theta was negative 3/5. So the opposite of negative 3/5 is going to be positive 3/5. And so the cotangent of negative theta is positive 3/5. Now just to show you real fast what would happen if you had to use the identities to do a problem like this instead of using the function definitions. I thought we'd just look at one. We're not going to go through it in detail because this is not how I want you to do them. It would take too long, but I thought I'd just show you what's involved. So what we're supposed to do here is notice that we have tangent and we want to find secant, so that makes us think of our Pythagorean identity that involves tangent squared and secant squared, and we would just plug this number in for the tangent there, so tangent squared theta would become negative 5/3 squared, and you add these together, and that would give you 34/9 equals secant squared. And then after a little more algebra to isolate the secant of theta, you would finally come up with secant of theta equals negative square root of 34/3. But this would take you a few minutes to work through all of this, and what we did back over here using the function definitions was so much easier and faster. You almost could do this in your head. So I just wanted you to see what you're avoiding by using the definitions instead of the identities. Now let's look at example 10 together, and this is our last one, and it's very similar to example 9. It says if tangent of theta equals negative square root of 6/2 and the cosine of theta is greater than 0, find the sine of theta. Now you know that we always start a problem like this by drawing our angle theta on the coordinate system, but they did not tell us what quadrant theta belongs in directly. They did give us enough information to figure out which quadrant theta is in. So they told us that the tangent of theta was this negative number here, so it has to be a quadrant where tangent is negative, and it also has to be a quadrant where cosine is positive. So that's going to have to be quadrant 4. So now here's a coordinate system. Let's draw ourselves a quadrant 4 angle and go ahead and close up that right triangle. Okay, now let's use the piece of information they gave us in the problem. They told us that the tangent was negative square root of 6/2. So if we remember the definition of tangent, now we know that the vertical side of our triangle is square root of 6 and the horizontal side is 2, and now we just need to find r. So we add the squares together. 2 squared is 4, square root of 6 squared is 6, 4 plus 6 is 10, so this r must be square root of 10. Okay, now to find the sine of theta, we remember that sine values are negative for fourth quadrant angles, and the definition of the sine function is y over r, so that's going to be negative square root of 6 over square root of 10. Now, that is the sine value, but we can't leave it like that. And there are a couple of different ways you could handle this. One way to handle it would be to go ahead and rationalize this denominator. So let's multiply top and bottom by square root of 10. Of course, that's going to give us a nice 10 in the denominator, but in the numerator, we have square root of 6 times 10. If you multiply those two together and get 60, you're going to have to break that 60 down. So instead of doing that, let me show you how I would do it. I would make myself one big radical for the top, and I would say that the 6 is going to break down into 3 times 2. The 10 is going to break down into 2 times 5. And there is our 10 in the denominator. Now, to simplify this radical, we've got a pair of 2's under the radical. So that's essentially 2 squared. So when that comes out of the radical, that's going to give us 2 outside the radical. And then that leaves under the radical 3 times 5, which is 15. And then we've got our 10 in the denominator. And now the fraction will simplify. 2 over 10 reduces to 1 over 5. And we end up with negative square root of 15 over 5. Okay, so that's it for section 5.1. And I hope that you will practice and get really comfortable simplifying expressions with trig functions and doing operations with trig functions, because we are going to use those skills a lot in section 5.2. So I'll see you next time. Bye-bye.